Hello everyone, it's Mr. Wolf here, and in this video I'm going to be modeling the thought process of number 3 with Mr. and Mrs. Turtle. So Mr. Turtle is riding on an electric scooter with some type of acceleration. So here is our scooter. Here's Mr. Turtle. Right. Then Mrs. Turtle, who makes the mass 1.5 times larger, hops on the scooter. So here's Mrs. Turtle. All right. Now both turtles are riding the scooter. The scooter exerts a force, so the net force is the same with or without Mrs. Turtle. So the power on the scooter is exerting the same net force with or without. So let's try to proportional reason with this problem. So number A is asking which variable besides mass is changing. So what I'm going to do is I'm just going to write my net force equation out. I know mass is increasing in this case, but it's asking what other variable is changing. So the best way to solve this is to figure out what variable is not changing. And again, the problem said that the net force stays the same with or without Mrs. Turtle. So I'm just going to kind of box in net force. So if net force stays the same, mass goes up, well then it must be acceleration that's changing. So I'm going to write acceleration. Now I also just thinking about this, since these variables are inversely related, since they're on opposite same side of the equation, if my mass goes up, well then my acceleration must be going down in this case. Right? For B, by what factor is the variable you identify different from when Mrs. Turtle jumps on the skateboard? All right, so now what I'm going to do is I'm going to use my same equation, F net equals ma, and now I'm not really given any actual values, so I'm going to put in my own values. Right? And if something stays the same, well, I'm just going to make this as simple as possible. If my net force is staying the same, I'm going to put in a 1. All right? I know that the mass, I don't know what their masses are, but I do know that when Mrs. Turtle's on the scooter, the mass is 50% more, or 1.5 times larger. And then I'm trying to see how much that acceleration changes by. So when we do 1 divided by 1.5, we get our acceleration to be, in this case, 0.66. Right. Now this 0.66 does not mean that this is their actual acceleration. It just means that comparatively, we could say their acceleration was 1 before, and so now the acceleration is 0.66. Well, that means that it's just 0.66 or 2/3 less than what it was before. So then we could actually figure out what the original, or what this new acceleration is going to be. The original net force was 5 newtons, and Mr. Turtle's was initially accelerating at -4 meters per second squared. All right, calculate the new value for the turtle. So let's see here. I'm going to say, all right, I got two numbers that I could either work with here: 5 newtons and -4 meters per second squared. And well, newtons, that's force, right? Meters per second squared, that's acceleration. So if I want to see by what factor the acceleration changes, I want to use this number right here. So this was the original acceleration when it was just Mr. Turtle riding it, -4 meters per second squared. And then what I'm going to do is I'm going to multiply it by the factor of change, 0.66. All right. So -4 times 0.66 is going to give me 2.64 meters per second squared. Now, it's also a negative, right? So this is being redundant, but negative means it's going to the left. I'm drawing an arrow that's going to the left. All right, so this kind of makes sense, because if my mass increases, my acceleration should go down, so this number should be less than -4. All right, and that makes also sense because if, like, my standard acceleration, if we imagine everything was originally 1, and then my acceleration is 0.66, then that's also going down as well.